So let's assume that you are going to launch a rocket. You worked hard on building it, and now as you put the rocket down, as it gets fueled, it launches off into the sky. Well, maybe not into the sky, but it launches high. As it keeps going higher, you'll notice its velocity starts to slow down as gravity goes in the opposite direction and slows it down. Eventually, it hits the turning point where from that point onwards, it goes downwards. Keeps going down till it finally hits the ground. That's okay. Everything has to come down at some point, unless it hits its escape velocity. So anyways, let's say you don't have the distance yet. All you measured from this rocket was the speed that it's going at in each and every single point. So let's say you have the speed of the rocket at this point, speed of the rocket at this point, here, here, here. So with this, you can now create a table regarding its speed and the time. So as you create the table, you would have time on this axis, and you would do speed. So in the beginning, it starts off at no velocity, but as you launch it up for acceleration, it immediately gets higher. However, as time passes, once again the gravity force comes into play, slowing down the speed. Then the speed slowly gets less and less, so finally it hits 0. And then after that, the speed reduces and goes in the negative direction, meaning it falls down, keeps falling down, till it finally hits the ground, speed becomes back at 0. So these are all the times plotted. But let's say you want to find the total distance that this rocket traveled, meaning this area. Of course, this is quite difficult to do because we don't actually have any desired formula for these shapes. It's not like a triangle or a rectangle where you can simply plug in the side lengths. So we need something else. This is where we introduce our new friend, integration. Now, believe it or not, integration can be used to find the area of any single kind of curved shape, such as in this instance. Before I get into integration, let me first talk about how we can actually derive it. So let's go back to this model. We're here. Now let's say you have this curve. If you have no idea whatsoever about how to calculate the exact area, you might try to find something close enough to it. In other words, you might try and approximate the area. So let's see if we can approximate the area. The first thing you might do is try to draw little rectangles in it, such as this, and then try to calculate their areas. So if I know the value of each of these, and if I know the width and length of each of these, I can calculate their individual areas and add them up. But as you can see, it's not going to be that accurate because there's still going to be this much area left over. So in other words, it's going to be an under approximation. So in an attempt to make it even more precise, you try something else. You try to use even smaller rectangles. So you start off with one, then you go up by a thinner one, and you keep doing this process. Now as you get here, as you can see, this is definitely a better approximation. We have a lot less remaining space. So one thing we could conclude from this very short activity is that as we make the rectangle length smaller, it actually becomes, we can actually fit more rectangles into whatever curved shape we're trying to find, or in fact into any kind of shape. It doesn't have to be this, it can be something like this. Either way, we can conclude that we can fit more rectangles into it, and thus we can better approximate the area. Now, if you don't believe me, you can try yourself and keep trying to get smaller and smaller rectangles. And by doing this, we actually get to the idea of integration. As I was saying, the smaller we make our rectangles, the better they approximate the area. So the integration actually extends this. What integration essentially relies on is that we are summing these rectangles, except there's a catch to it. The width of the rectangle is approaching 0. So what does this mean? Of course, the width isn't exactly 0 because that means the rectangles would be non-existent, but the width is so small, infinitesimally small, that it's almost approaching 0, yet still it can't be considered 0. And what we call this is dx. Now, d is what we would call it, and then after we would put the variable that we're using. So for example, if we denote the width by the variable x, right, because maybe our width is through the time axis, right, and the time is on the x-axis, so we could denote it by the letter x. So that would be called dx. And dfx essentially says that we're taking an extremely small portion of x. That's nearing towards 0. Now, I'm hoping you should be familiar with this, because if you're watching this video about integration, you would obviously most likely need to know differentiation and limits before this. So hopefully you're familiar with the idea of approaching to 0, and you don't need much further explanation. So approaching to 0, dx. So you'd see, according to integration, once you make the width of these rectangles dx, they become so thin that you can exactly fit them to represent the curve. So if we have the curve, the width of these rectangles would be infinitesimal. So it's almost like we're adding the rectangles here, as you can see, and they would exactly approximate this area. That's the whole idea. Okay? But one thing you might notice is that the smaller you make the width, the more rectangles you would have to fit in. Right? And if you think about it, you can see that as you make the width of the rectangle closer to 0, you need more rectangles. Specifically, as you make the width of the rectangle nearer to 0, nearer to dx, you would need an infinite amount of rectangles. The closer it goes to 0 for the width, the closer the amount of rectangles required goes to infinity. Now, because of this, we get integration. This is exactly what integration is. So let me just define. Integration is the infinite summation of triangles. Sorry, not triangles. I apologize for that. Not triangles, of rectangles with a width of that approaches 0. So that's what integration is. Now, we might have the definition, but how might we actually translate this into words? So let me help you out a bit. When we talk about integration and the infinite sum, what we would actually use, since you can see that integration is clearly the summation of these infinite rectangles with a very thin width, the sign we would actually use for summation is not exactly the addition sign, but rather we would use this sign. And now what we would do is, when we have these rectangles, firstly, how might we find the area of a rectangle? Well, firstly, of course we know it's the width times the height. But what exactly does that mean in a scenario where we have a graph? What does that mean? So as we already defined in integration, the width would be dx, approaching 0. But what about the height? Well, for the height, you'll notice that the height can actually be represented as f of x, assuming we're using the variable x, right? And the reason it's f of x is because the height is simply what function is simply the height you get in the function itself, right? When you have this rectangle and you input an x value, you get a certain y value, and that is simply the height of this rectangle. So you can actually denote the height of the rectangle as being f of x times d of x, where d of x is the width and f of x is the height. So with that in mind, we can now move on and further progress with the summation. Now, since we're summing an infinite number of rectangles, it would clearly be too tireless if we said rectangle 1 plus rectangle 2 plus rectangle 3. So instead, what we can do is we can do this. Firstly, when we're finding the summation, we have to consider what area or what interval we want to do it on. So for this, if I want to find the area for a graph like this, of course, if the interval here is 0 and the interval here is 10, and I want to find the whole area of this, I would of course use the interval of 0 and 10, right? But if I only wanted to find the area of half of this, which could be 5 here, I would use the interval 0 to 5. So, with that in mind, essentially what this integration symbol is doing is it's saying we're infinitely summing the rectangles. And now, what is the area of the rectangle? F of x times d of x. Okay? And then now on the top we put two numbers actually. These numbers are the intervals that we're summing it from. So let's say I want to find the area of half of this. So the interval could be x equals 0, x equals 5. So I'm summing from 0 to 5. So once again, let me just quickly break this down. What this formula is saying is that we are taking the sum, infinite sum, right, of rectangles which have infinitely small width, right, of these rectangles. And then once we're taking it, we need to specify which interval we're doing it against. So we're doing it from the interval, on the interval. In our case, it would be x equals 0 to x equals 5. So that's the interval we're doing it for. So this is the main conceptual part about integration. I hope you were able to learn something from this. If you did get confused, please feel free to drop down any questions and I'll try to understand them. And I'll try to answer them, But the main part with that you get is that integration is simply a way of finding the area for curved shapes. And you simply do it by making your approximations closer and closer to the actual value, which is by reducing the width of your rectangles, if we take rectangles as our shape that we're using to approximate with. So yeah, I hope you understood it. In the next video I post, I will definitely go through some problems. However, it is very essential that you understand the intuition so that you can be able to solve even harder problems and just in general understand the concept. So thank you. Have a good day.